Projectile motion questions can be divided into three different types. Type 1, Type 2, Type 3. These are very unofficial designations, but lots of people use it and it's handy. So Type 1 tends to be the simplest, and let's look at the problem here. Rock is thrown to the ocean. Well, with every projectile motion question, I highly advise you first start drawing a labeled diagram of what's being described. You have your two dimensions, your vertical and your horizontal. It'd be pretty easy to mix them up. Here, the vertical, which I'll call an X dimension, is what we're looking for. This is the height, and we're told that's 60 meters tall, and that's a Y dimension matter there, the vertical. Step 1, always draw a label diagram, and it's thrown directly off with a speed of 13 meters per second. Step 2, separate your dimensions. They are independent of each other. The side to side and the up down, the X and the Y dimensions. Now, I'm going to say 100% of the time in the X dimension, there's only one equation that you ever really need. V equals d over t. There is no acceleration in the X dimension. Gravity doesn't pull sideways. Gravity only pulls up and down. Now, in the Y dimension, any one of your acceleration formulas could work, but I'm going to suggest, look at this one first. It's probably going to be it. And for that matter, I'm going to say the initial velocity is 0. So the whole equation reduces to a simpler form. Now, how can I say the initial velocity is 0 when it clearly says 13 here? Well, the initial in the Y is 0. This thing is thrown sideways, not thrown downwards. So initially, downwards is 0. And it doesn't matter about the sideways velocity as far as the up-down is concerned. So step 1, label diagram. Step 2, a chart for the dimensions. Step 3, even if it doesn't ask for it, solve for time. You need it 99% of the time. Step 3, even if it doesn't ask for it, solve for time. You need it 99% of the time, might as well solve it. Now, I see time here, I see time there. Where should I do? Could I solve for time here? Well, not quite, because I don't know this distance here, the X dimension, I don't know it. But I know the Y dimension distance, so I'll solve for time here. So a little bit of algebra, twice d over a under a square root. I'm ready to go there with some substitution. Twice the vertical distance of 60 meters over acceleration due to gravity, 9.1 meters per second squared. Don't forget to square root it. Now, I can say that down is negative, and there's nothing wrong with that. If that's the case, that should be a negative. But if that's a negative, this should also be a negative because it's going downwards. These two will cancel each other out. So how long is it in the air for? That's what I need. So 2 times 60 is 120 divided by 9.81 equals, don't forget to square root it. It is in the air for 3.497, let's say 49 seconds. Okay, if you actually did, just hang it up. So again, typically step 1, label diagram. Step 2, the chart with the two dimensions in it. Step 3, solve for time. And typically you solve for time in one dimension, you end up using it in the other. So over here, I'll see about using that time. So d equals, well, the v in the X dimension is 13 meters per second. The time in the air is the only quantity you can count on being the same in both dimensions. 3.497, etc. seconds. D is equal to, so times 13 equals, and then we have our d of 45.467 meters. So the distance traveled along the horizontal there is going to be two significant digits here. Let's say 3 significant digits. I'm going to say 45.5 meters. And that's it.